My slide is visible.
Yeah, it's good.
Yeah. Thank you very much. My heartfelt thank you, and I'm very much grateful to Professor Krishna Reddy for giving me such a great opportunity to share our work here. And our mission is to create awareness about the tsunami and need of the tsunami research. So a very good, warm good evening from India. And in India, we are right now celebrating, as Professor already said, Krishna Janmashtami. So on this occasion, I wish you all the attendee and all over the world very happy, peaceful, and very successful life ahead to all the attendees. And yes, Professor Krishna Reddy's name is also linked with the Lord Krishna. Today is the birthday of Lord Krishna, God Krishna. So in this way, we are linked. So thank you very much once again. I would like to start my presentation. The topic is novel mitigation technique for earthquake and tsunami-induced geo-disaster. State towards protection of coastal area from tsunamis. Myself, Babloo Chaudhary. I am at National Institute of Technology, NIT, Surathkal, India. So I will quickly, yes.
If you go back a little bit, go back to the previous slide. And then that at top, we're seeing some black line, maybe, yeah, that one. Can you move or hide it? Yeah, now it's good. Now it's good. Thank you.
Thank you very much.
And then I also see that, yeah, if you can hide that thing, we can still see that one, yeah. Go and yeah, right click there. Yeah, now it's perfect.
Thank you very much. So I would like to quickly finish this content, starting from background. Tsunami is not much known things. So I would like to introduce a basic, very basic. Then what are the damage caused by the past tsunami all over the world, especially some major countries affected by tsunami that we'll see. And then what are the challenges ahead for us as a civil engineer, we will try to see. And then what are the, we have developed the countermeasure, what are the, we have, so that we can protect our coastal area or our community from such a devastating damage caused by the tsunami. And then finally, what is the conclusion? So let me start with a very basic introduction. Tsunami, actually, it is a Japanese word named tsunami. It's a harbor wave. So it's a series of water body caused by displacement of large volume of water, generally in ocean. But it can be occur in large water body anywhere. Basically, it happened due to the vertically displacement of the overlying water. So tsunami most often caused by the earthquake, but it can be generated by the landslide, volcanic eruption, or any such impact which can abruptly vertical displace the water. Tsunami act as a very fast rising flood, and it strike our structure with a very devastating force. So this is unlike earthquake. Many people are confused. Like earthquake remains for a few seconds, only 10, 20, 30 seconds hardly. But the tsunami can continue for hours. And it is very important to understand first wave may not be the last, or first wave may not be the largest. So even especially when we are in trip somewhere, then in that case, if you save ourselves from first wave, it's not be the stop. So what happening when the tsunami is reaching toward the shallow depth water, it's a spike, the height increases. However, in deep sea layer, there was a height was less. It was the reason. It is the reason when the some sheep are in the deep sea, then the tsunami can cross unnoticeable. So. So this is an example of tsunami. one available in emission video. So this is a bed of the seabed, bedrock. We can see the earthquake strike, and there was tectonic movement. Large amount of tectonic plates move upward that force the seawater upward direction. Finally, this is the tsunami wave generating from the origin, and it moves all around away from the origin. Once it reaches towards the shallow depth, its height will be increased. Please note down, this is the most devastating, and it is a kind of trap for the human beings which are on the beach. But when generally in the sea waves going and coming around 10-15 meters, but in the case of tsunami, this is the unusual downward movement of the tsunami water, maybe 30-40 meters. If you, yeah, so this is an indication. So nature gives the indication now tsunami is coming. But the thing is, many people who are on the beach, they rush to catch the fishes and rare sea animal, and that is the killing point. That is a just suicide like thing. So this is a early warning system by the nature. Such unreasonable or some unusual movement of downward seawater going on means this is a clear indication of the tsunami coming. At that time, don't run away. You find the higher height. This is different from the earthquake. So if you run away, hardly you can run, or 1 kilometer, 2 kilometer. Even you have some vehicle, you can catch the vehicle, you can go within 1 to 2 kilometer traffic jam or other. Better to go some higher rise place. So this is, I have again started the videos. So this is going down the sea water. Now we can see the tsunami water is coming. The tsunami wave is coming with a very high force, very high speed, and it going to strike whatever coming inside is going to flow away, vast away, and it can take away. Again, please note down, this is the first wave. So don't think first wave is the last wave, or the first wave is the largest, highest wave. Second wave can be largest, third wave, and so on. So even if we save ourselves in first wave, we should not be very much safe. Now we are safe. We should wait till the whole system subside, tsunami, and or some official announcement should be made. Once again, I repeating here. After unusual going down, tsunami is coming. And it is a series of waves. It can continue for hours, maybe 5 hours, 6 hours, and sometimes can be day to subside the tsunami water. So please take care whenever you are on the beach. One thing I would like to mention at the last slide is the most important. That is nothing related to research, but it can save your life whenever you interrupt some. So please wait till the last slide. So this is the one devastating damage occurred in 2011 Great East Japan earthquake tsunami. This is a real picture captured by the helicopter by Japanese personnel. So we can see this. This is the first wave of tsunami is coming. This is the second wave. Third wave on. Some sound you can hear. Japanese. So this is the tsunami wave reaching toward the seashore.
大きな津波が複数波に分けて現在海岸に押し寄せているのが確認できます。
Time is 11 March 2011. And this is the tsunami wave already reached on the seashore. We can see the whatever the building or any structure, natural or artificial coming is the tsunami water. This is going to be drawn down, devastated completely. You can see here one big building is there. Let's see what happened with this tsunami water. What could the damage or the building can survive such tsunami waves. You can see here all the buildings and the whatever the concrete, steel or wooden structure going to be completely collapsed, and it become the more devastating when it is this is now coming toward the whatever the coming in this way, either the industrial sets, some industry sets, farmland, rice field, paddy field, houses, any structure that is going to be collapsed. And this is the water is most dangerous for us to design a structure. When the water is plain, when they're striking from the sea, the water is only water. Now the tsunami water is mixed with lots of debris, wood blocks, concrete blocks, iron metallic things, and with this, if it strike our foundation or any building, you can understand, you can imagine how much impact force will be going to suffer. So these are the some country having the maximum number of tsunami. You can see here Japan. This is just one statistics. Today I have just downloaded from the internet. Japan 140 times, 143 times. Maybe it is the recorded history. Previous recorded history may be many high. Indonesia 77 times, United States 74 times, Italy, Chile, Greece, Peru, or some other country which has been affected, India, Canada, Russia, Sri Lanka, Taiwan, list is going on. So almost all the countries which are surrounded by the sea or having the earthquake prone zone have been heavily affected by the tsunami. So this is the 10 worst tsunami occurred in the history. So unfortunately, first is the Indian Ocean earthquake tsunami, and these are the 10. If we see out of 10, 1, 2, 3, 4, 5, 6 are from Japan. So in coming slide, I will give some example. I will show you some pictorial pictures so we can imagine the devastation of this thing. So let us start from the 2004 Indian Ocean earthquake. So the tsunami height was up to 30 meters. A number of countries affected by 14 countries. And Richter scale, magnitude scale, the earthquake was 9.1 to 9.3. It happened 26 December 2004. So here it is around Java, Indonesia. Here the earthquake strike and tsunami will generate from here, and whole eastern part of the India was heavily affected. Here the Sri Lanka, that was also heavily affected. In fact, the Kerala, which is sitting on the western side of this India, was also affected. The reason is deflection. So this is the affected country, around 14 countries. Height goes up to the 30 meter, 10 meter, 5 meter, like that. And this is just one indication. The death and the estimated death might have gone very high than this list. So this is some devastating image. We can say this is a very beautiful landscape before tsunami, and everything was washed away. Only devastation remained after the tsunami. This is again very beautiful landscape here, but remains only the devastation. Same here. You can see some aeroplane can land over our houses. It might be floated by the tsunami wave, and this is the way scale of the devastation after the tsunami. Now, this was the 2004. Now, I am giving you some example of 2011, that is Japan earthquake and tsunami. So this was also around 40.5 meter recorded in Miyako, Iwate Prefecture, Japan, and earthquake was generated, which generated the tsunami was 9.9 to 9.1 Richter scale magnitude moment. So we'll discuss here damage because Japan is very good for record keeping. So we'll see, because for research we need the how much height of the tsunami, due to that what are the damage occur. Then only we can do some simulation. We can create similar situation in our lab. We can do this research, find out the reason. Then we can able to find out the countermeasure. We will discuss here damage of the structure or any buildings, drifting, overturning, collapse of wall, erosion, scoring, and debris impact. So this is the left top side is a pioneer picture of the 2011 Great Japan earthquake. We can see the big vehicles or even car behave like a choice. This is the building, concrete structure, maybe steel structure, and ship is landing over the one building. We can see the building seems structurally sound, but due to the foundation failure, it was completely damaged. Here, this building again damaged, that the height was 9.5 meter. This was it looks a highway, some bridge. Here, again 8.5 meter, you can see how much devastation occurred. It was the bridge, so the whole deck was passed away, only the pillar remains there. This is again a big matter of discussion and research we need. Here we can see there was one building here. This was drifted here. If we count the opening 1, 2, 3, 4, it looks around 4-story building. And we can see there that this is pile founded building. We say the pile founded building is the strongest building. And we can see the pile is cracked and still hanging over. Now, what is the beauty of this? Or we can say the hard luck. There was a road and this building was dragged from here and there was no stretch on the road. That means it was drifting. It was shifted by the buoyancy force, by the tsunami force, and was laid over this. So this again opened one new area of the geotechnical engineering to determine the bearing capacity for tsunami. Right now, no country have any codal provision or any countermeasure how to design a cellar foundation or pile foundation by considering a tsunami. For example, somebody want or some country want to make a tsunami resilient structure. For example, nuclear power plant, we want to make it tsunami resistant. There is no codal provision. Even ASC was planning to do. They have some recommendation only. So we need a good amount of research. Like earthquake, everywhere it is sandwich, either shallow foundation, deep foundation, bridge, road, highway, everywhere sandwich. Like tsunami also, in coastal region, we have all type of infrastructure, highway, railway, building, hospital, everything. So here also we have to do the research for the tsunami as well. If somebody want or some government want, then we have to come over to give the solution. So again here we can see the building structurally looks sound, but due to the foundation, these were triple. Here again it was pile founded, but damage occur. Same these here. So these are some coastal structure. Now these were the onshore structure damage. This is the offshore structure. We can say luckily this building saved by this big ship. This is the sea wall damaged by the tsunami. This is the world deepest breakwater, that is 64 meter around deep, Tamashi Port, Japan. This is the tsunami resistant made in 2009. Just after 2 years, it was damaged. So this is the before tsunami. This is the after tsunami. Why it damaged? Even it built as an earthquake proof, tsunami proof. That also we will discuss. So now, this is one thing, what we can develop our countermeasure, we can block, how to block the tsunami, how can protect our thing. But when the tsunami coming on this our land, then there was a big geo-environmental issue. That is, tsunami has a devastating impact on the human life, causing injury, death, widespread destruction of human, business, infrastructure, and all. Agriculture field, either aquaculture areas, forest, mangrove, coastal area, wetland, coral reef, etc. Everywhere they are badly damaged. So finally, tsunami water that will come with the pollutant, with lots of the dead bodies of animals or human beings, toxic substances, sediments, marine debris, and invasive species that can harm our agriculture land, natural resources. Finally, this can lead to a loss of biodiversity as well as can lead to destruction of the complete ecosystem of the coastal area. So major issue remains with us, what to do with this tsunami, disaster debris. After tsunami water recedes, going back again to the sea, this type of debris remains. Tsunami debris will remain like that. It can be contaminated soil with the many soil tank might be there. It can be leaked with some chemicals. It will spread about the soil. It can be contaminated the water. It can be contaminated our soil. It can be contaminated the groundwater system. It can create this is a geohazard contamination like Fukushima nuclear power plant melting, something happened. Means again, this type of soil, neither they are used suitable for the agriculture, not making for any small scale of foundation. So this is the next level of research that again the new research coming in the area. We have to do the geo-environmental issues, research, so that we can make it suitable for our structure. Because our town, our village, our area can be filled up this type of things. So maybe some professor are working, like Professor Katsumi, who is giving the webinar next Thursday. Maybe he can put some light on this area. So here I am going to discuss how to prevent such damage, or we can say the how to block the tsunami-induced damage. Then, yes, what are the possibilities? What are the resources we have? We can have the structural countermeasures as well as the non-structural countermeasures. Structural countermeasures include, we can have a tsunami breakwater. We'll discuss what is tsunami breakwater. I will show you some photographs. Tsunami seawall, tsunami floodgate, buffer block, tsunami evacuation building, or tsunami forest. Non-structural countermeasure can have multi-layer approach. We should have the proper monitoring system, early warning system, before we have the evacuation plan, so that at the tsunami will get hardly half an hour, 1 hour. Within such a small time, it should be well-defined path so that people can run away. Otherwise, traffic and people can entrap. Coastal planning and public awareness. So here, today we'll discuss about the tsunami breakwater. What is the breakwater? Breakwater is nothing but a wall-like structure. It's laying over the seabed, close to your seabed coastal area. So what is the purpose? To prevent any disturbance coming from the seaside. So the harbor side, so water is calm and cool. However, there is some opening here, through that sea and cargo can come. So mostly the breakwater are built over the near the port and harbor, so that the cargo and ship operation can be happen in port. But if you want to protect some area or our city, or if you have a nuclear power plant, we can cover like that, and we make it tsunami resilient, assistant. If the tsunami is striking here and strike and go back, in this way we can say we can block our tsunami in the sea itself. If the tsunami is not coming on the land, means we are safe. We can save our infrastructure. After 2011, there was great debate how to protect. So these are some seawall made in Japan. This is built to withstand 19 meters of tsunami at Hamoka nuclear power plant in Japan. This is another barricading structure, tsunami seawall. We can see, if we see the 5 feet, 1.5 meter average height of the one person, means it's maybe around 20 meter height. It can protect up to around 20 meter height of the tsunami. But this type of a structure people don't like, because this is a blocking. The on-side people can't see the sea and they can't feel comfortable. But this is, of course, one way to protect our coastal area from the tsunami. Another is a floodgate. So if some early warning system coming, or if we are coming to know some tsunami is coming, we can close this gate, and whenever the tsunami recedes or there is no chance of tsunami, you can open for public use. This type of gate is also there. During normal times, ship and cargo can float. However, in the time of tsunami, we can lower down so that we can protect this type port area. Again, this type of floodgate is also possible. So these are the things. In general, basic things I have discussed. Now coming to the technical point, discussing about the tsunami breakwater here. So breakwater, what is a breakwater? Breakwater is a offshore structure, or say coastal structure, constructed to protect the port area from the sea wave, current, typhoon, and tsunami. You can see the seaside, there are lots of eddies and disturbance. Over the harbor side is cool and calm, but here is the opening. So ship and cargo can shelter. Similarly, if we make the tsunami resistant, it can protect the whole area from tsunami. Basically, this is a composite cation type breakwater. So for this making, we put a large amount of rubble and big stone over the seabed, and over the plain surface of this, we give the large number of cation along this, and finally we fill the gap. It will behave as a retaining wall type system. Later we can fill this cation with the sand or any material, so that it becomes heavy to stability, gain the stability. So I will show you one example what happened, and whatever we have developed the countermeasure. So this is the 2011, it is Japan earthquake intensity map. Here the epicenter, this red area was heavily damaged. Similarly, you see the tsunami origin here, and the red line is showing the height of tsunami, and this is lower, this is the lower. If we see, these are the most affected area by earthquake and tsunami. And these are the major port of Japan happening in those areas. So if we want to see the breakwater, what is the breakwater here? These are the port time, length of the breakwater, damage length of the breakwater, damage percentage. If we see, almost all the breakwater was heavily damaged. So the survey will continue, and Kazama and Noda found that these are the main reason of damage of the breakwater. If we see, most of the breakwater was filled due to the scouring of the mount or sliding of the cation. So this was happened due to the foundation failure. So this was due to the foundation, means the ball was in the court of the geotechnical people. They didn't have much significant structural damage. So we, the geotechnical people, had to come up to give the solution, because world, our society wanted solution. So this is, I will give you an example, port breakwater. This is the breakwater before, and this is the breakwater after the earthquake. This is the world deepest breakwater, 63 meter depth. And this breakwater was damaged around 74% by length due to this earthquake and tsunami. If you see the satellite picture, large amount of the cation was slid from the mount and sinking into the sea. You see this photograph. So this is the hypothesis or some reason come forward by the port and a port research institute party. So this is the breakwater, this is the seaside, herbal side. So the main reason of the damage of the breakwater was large difference of seawater from the front and back of the breakwater. It was around 8.2 meter high at that time. There was a high tsunami impact force over the breakwater. There was a scouring of the mount and a strong flow between the joint. In addition, we found in our research that seepage was also the major impact of reason of the failure of the breakwater. I would like to mention here, due to the failure of this breakwater, tsunami wave could not be blocked by this breakwater and enter in the Kamaisi area, and more than 800 people died due to this. However, this breakwater was made tsunami resistant, but at that time, the height of the tsunami was, design height of the tsunami was 5 meters, but the tsunami strike at that time was 8.2 meters. Of course, there was no chance for survival. That's why it failed. So after that hypothesis started, so even if the tsunami exceeded the design height of the tsunami, the structure should not collapse completely. It could serve. So on that principle, we have developed some countermeasure. So the reason, the challenge was to develop reinforcing countermeasure for the breakwater foundation, which can make breakwater resilient against earthquake and tsunami. Because tsunami never come alone, as we all knowing. Before tsunami, earthquake is coming, that making a very big complex, because here around after 8 minutes of the earthquake, tsunami came. So during the earthquake, the whole system, because seabed was fully saturated, so and it was a coastal area, so the earthquake itself damaged, and after that, if the tsunami is coming, it was a very, very complex phenomenon, and the breakwater was unstable. Again, the next level of the devastating force acting, so it become a more fragile, and it finally damaged. So this is a really very, very complex to understand, and we need a large amount of research so that things should be clear. Some research started, but we need more and more so that things will be clear. So here we have developed some countermeasure. We have done some experimental, analytical, numerical study. We have developed some new apparatus. We have used some industrial waste material like iron slag. We have done shaking table test, hydraulic model test, centrifuge model test. And now coming to, before going to see, this is based on our research. We have done number of experiments for only earthquake, then we give the tsunami so that we can understand what was actually happening. Once we able to understand the reason or mechanism, we can able to find the solution. This is the fundamental thing. So we have done lots of experiment. Based on our experiment and literature review, here I would like to summarize what could happen to the breakwater when the earthquake coming, then tsunami coming. So during earthquake, this is the excess pore water pressure can generate in the foundation. The seismic inertia force will act on the breakwater, and then finally it may deform. In the case of tsunami, after that, already breakwater is deformed condition. Under unstable condition, the excess pore water pressure may not dissipate completely at the time of the tsunami arrival, and after that, the tsunami wave is acting, tsunami force acting on the breakwater. Due to the overflowing of the tsunami, a scoring may occur in this area. Due to the water level difference between front and back of the breakwater, seepage is quite expected because this is made of the rubble, and due to the high seepage, piping may occur. So combined action of all these, high deformation, high scoring is expected. Now the challenge was we have to make some countermeasure. The big challenge is, so here by this experiment, we have found some new fact explored. We have found the tsunami-induced seepage, and piping was one of the most predominant reason for the failures. Again, rubble mound here that made of the rubble mound that was also sinking due to the high seepage force and tsunami-induced liquefaction. Before we knew that earthquake-induced liquefaction, but in this research with 1G model test as well as the centrifuge model test, we could able to prove tsunami also generated liquefaction. So these become extremely complex phenomenon. And this is our conventional breakwater. Now we have to develop the countermeasures so that it can protect this during earthquake, tsunami. My dear professor and my dear friend, both earthquake and tsunami is completely different, actually opposite. Earthquake, heavy material if you put, seismic inertia force will be high and more damage can occur. But here, to prevent scoring, we want heavy material to be here so that scoring can be prevented. So both are vice versa. So we have to manage somehow so that it can be managed. We have developed so many models, techniques. We tested for earthquake, many were successful. Then we went for the tsunami, some techniques who were successful in the earthquake but failed during the tsunami because both the phenomena are completely different, but few are successful. So only the models or method which was successful for both earthquake, tsunami, we adopted for combined action. So here, this is the combined rubble mound. This is the seabed of 2 layers, rubble mound and cation breakwater. And as a countermeasure, we insert the rows of the seat pile at both the sides. It will prevent the lateral deformation of the ground during the earthquake, as well as it can behave as a cut-off wall during tsunami. It can prevent the seepage through the seabed. After that, we cover the whole rubble mound with number of gabion. The reason was the gabion was heavier than the rubble mound. We use same rubble mound fixed with the iron cage and fill it so that during the overflowing tsunami, it may not scour easily. In addition, we have developed a special type of gabion. So sea side, we have a special type of gabion, harbor side, normal type gabion, because the one reason was high seepage from the sea side to the harbor side. So what we have put? We have put a small thin metallic plate over the top, only sea side. So what is the purpose? Purpose is to make it impermeable. So this can be replaced by any impermeable material, can be geomembrane, can be plastic material, can be any material which can impermeable. But yes, between two gabions, it might be some space, but till with that space also, it can able to prevent 90 or 95% seepage. So if we are not allowing to enter the seepage from here, then one also devastating damage we can able to stop. However, here we didn't allow any special type given because if some water is coming, we allow the water to go away. Otherwise, it can erode our things. And in addition, we provide a geo-grid layer so that during the earthquake, whole ground will set and it tries to settle down. At that time, the geogrid with the confinement, it will not allow to settle down. At the same time, during the tsunami, we mentioned that this rubble mound, this rubble, big boulders also sinking inside the sea due to the very high seepage, because the seepage high water head was sometimes 10 meters or more. So we can imagine the seepage force was can be very high. So this opening of the geogrid will be less than the size of this one. So that also prevent. These are the some of the model we have developed. This is the unconventional unreduced force or conventional breakwater, 2 layer of seabed, caisson and rubble mound. And here we provide the 4 rows of sheet pile, 2 inside, 2 outside, and a numbers of gabions. Here we have provide 2 rows of breakwater, rows of sheet piles only, 2 rows of sheet piles with geogrid. Since this is a very huge, very huge structure. Depth can be 20, 30, 40 meters. Length can be in 1 kilometer, 2 kilometers. It's like a dam, heavy dam. So if I can't say any government or we researcher can't say any government, no, this is a vulnerable, it can fail. So you demolish this breakwater, make new breakwater. No, nobody will going to buy our research articles. So we have developed some countermeasure which can directly implemented on the existing breakwater, like this 2 rows of breakwater. Here 2 rows of sheet pile we put at the top side lid and we can fill the gabions here. This also can be done with the existing breakwater, as well as some new breakwater. We have all the facility during the construction. We can provide the geogrid and some more advanced model we have. So to check how much effective it is, we have taken the real ground breakwater, that is a Miyazaki port, and the prototype to scale ratio was 64. This is the 3D model of the breakwater. We have done the 1G model test, sectable test, hydraulic model test. The lower sand was the dense sand layer, relative density 90%. Upper seabed layer was 60%. These are the rubble. These are the gabion, normal gabion. This is a special type of gabion. You see the caisson we have provided, 3 caisson we have provided, and all the instrumentation we have provided for the main caisson, so that any side impact or the boundary condition can be prevented. And so first we gave the earthquake to simulate the real ground condition. So since earthquake has a strong earthquake only impact have to generate the tsunami. So our tsunami generating earthquake is very strong. Generally they have the foreshore and main shock. So almost maximum possibility we try to accommodate in our research. We give the foreshore and main shock 0.1G and 0.3G. Acceleration frequency was 0.65 and the shaking time was around 3 meters. And this is prototype, corresponding model type, main shock and foreshock we have given. This is the instrumentation. This is the 2 layers of seabed. We measure in this experiment vertical settlement at 2 locations, horizontal displacement of 2 locations, pore water pressure at 10 locations, and acceleration at 7 locations, and water tsunami pressure at these 4 locations. So we develop a new apparatus, maybe first time in the world. So generally we know the tsunami flume is very big, and set table has 2 meters, 3 meters, 5 meters. How we can put the tsunami flume on the earthquake for check table? Because after first earthquake occur, the building or the breakwater can deform. After that, on that deformed condition only tsunami should happen. Then only it will represent the real ground condition. Otherwise, it is not the real ground representation. So we develop a new type of system for tsunami generation. This is proved many paper publication and all over the world. Many people later they have followed or similar they have also followed. So we have imported 2 water tank both sides, and we put the water pump, one for inlet, one for outlet. We allow the water to in, and from that it is overflowing, striking the breakwater and coming here. And to prevent the reflection of the tsunami wave, another pump is sucking the water and sending it back. So this is the first we give the earthquake, and we let the model completely deform as per the natural status, and after some time we give the tsunami. So here we give the earthquake, here the unreinforced case, and this is the one reinforced case. We can see there is more than 50% reduction in the average settlement. We measure settlement as V1 and V2. We have taken average, and average horizontal displacement around more than 90% was reduced. As you remember, Kamasi breakwater fell due to the lateral movement sliding of the caisson. So by using this type of countermeasure, we can prevent the sliding. Here it is for during the earthquake. After earthquake, we gave the tsunami overflow of about 10-meter high tsunami. During tsunami overflow, this is for black color line is for the unreinforced case, red color line for the reinforced case. Here also. So this is for settlement, this is for horizontal displacement. So here you can say the settlement can be reduced more than 50% during tsunami, and horizontal displacement again can be about 90% reduction in the horizontal displacement during the tsunami overflow. This is the photograph taken after the earthquake in tsunami. We can see there, this is the unreinforced foundation, this is the reinforced foundation, highly settlement, highest power, this is the less settlement, almost negligible power. If you measure this in the prototype scale, it is around 15-meter wide and 5-meter depth. However, here, negligible. And we have done some seepage analysis by the flag to the, and we can find here the high seepage we can find here below this caisson, because this part is made of the rubble and top layer was loose sand layer. There are high seepage. However, by using this seed pile, you can see the seepage is coming there and where, and very less seepage was here. So what is our hypothesis? It will act as a cutoff wall, and a special type of gabion both perform excellent to prevent seepage. Finally, we can get the resilient condition. So this is the 1G model test. After that, we have done the centrifuge model test. So whatever we have done before, discussed before, it was a standard average breakwater, that is the height of around 20 meters. This is a Kamasi breakwater, deepest breakwater. We wanted to check our countermeasure. Is it suitable for average height of breakwater or deepest breakwater, deepest breakwater? So we did same thing, centrifuge model test at DPRI Kyoto University at 25G gravitational field. This is the unreinforced condition. This is the with a reinforced condition. You can see the caisson was completely a resilient condition with the tsunami. This is a dam break type of method. By using this, we generate the tsunami. That proves our countermeasure is well effective. So this is was a caisson type breakwater that happened. One type of breakwater happened mostly. The caisson type of breakwater is very costly, mostly in developed country. But most of the developing country, other country, they don't have the caisson type of breakwater. They have a different type of breakwater. Especially as I can see, many researchers are from India. So why such tsunami, related research is really important for India or not? Let's have a look. And why we utmost need, this is a wake-up point to wake up. All the researchers come forward, join our hand, and let's build our tsunami resilient society. So we have already faced devastating damage during 2004 Indian Ocean earthquake tsunami, as we discussed. But as per now, if I ask a poll, which coastal area, eastern coast of India or western coast of India, which coast of India is more vulnerable around for the tsunami? I am very much sure 95% people say eastern coast of India is more vulnerable against the tsunami, but it is wrong. Western coast is more prone towards tsunami. Why? Let's see. So due to this earthquake tsunami, almost all the eastern coast of India will suffer a lot. This is the tectonic plate. This is fault zone around India. We can see this is surrounded by the India. This is Indian plate. And there is a Makran subduction zone. Maybe very few people is knowing. If I enlarge this here, Then this is the Makran subduction zone. This is the, sorry. This is the Makran subduction zone. This is the Kutch, Gujarat, and this is a very active zone. Due to this zone, this is a tsunami subduction, sorry, earthquake subduction, the Makran subduction zone. They had potential to generate a very high height of tsunami. In fact, World Tsunami Association is very much worried for this tsunami subduction zone. In fact, it is already generate very high height of tsunami. As we can see here, the cause of 40 feet tidal wave when November 29, 1945, where this is happened around Karachi. Karachi is in Japan, Pakistan, but geographically it is very close to the Gujarat and western coast. So already 1945, we had around 13-meter high tsunami strike over the western coast. Height of tsunami was around 11 meters on Mumbai port, Mumbai coastal zone. So western coast already suffered tsunami high. On the other hand, 2004, eastern coast has already suffered a high height of tsunami. If I want to see the occurrence or return period comparison between earthquake and tsunami, and here is the earthquake. If I see in India major earthquake occur in Bihar, Nepal earthquake in 1934, later there was a Bhuj earthquake, significant earthquake I am asking, talking about 2001. Return period is 67, but tsunami 94 and Indian Ocean tsunami for 59 years. So if I see here, tsunami occurrence is high frequent. And this Makran subduction zone, already tsunami generated earthquake not only happened in 1945 period, also already they had maybe in prehistorical time also. So please wake up, my dear friend, my dear researcher. We have to wake up. We have to do research. It is not like that I am giving you the less value of the earthquake. For tsunami, first we have to face the earthquake, cross the earthquake, then we have to come the tsunami, then develop for the tsunami. So we have to develop all the infrastructure, either coastal. We have so many nuclear power plants in India, Tarapur, Kundakulam, all the nuclear power. Something happened, bad means what could we can imagine. All type of infrastructure already mentioned, school, colleges, bridge, highway, hospital, everything. If someone if government I want to make give me the tsunami countermeasure or what are the guideline, I use code, any code. As of my best of knowledge, no codal provision are available. However, for earthquake, we have some guideline, we have some countermeasure we can use. So for that, this is the infant level tsunami related research. So we can do research for any shallow foundation also, pipe foundation design also, and how much it can affect, how much we can design, how we can accommodate in design. That a matter of good discussion. So as we discussed already, probably no codal guidelines are there. There is no countermeasure almost, and so we have to develop the countermeasure as well as the countermeasure develop. So once I was finished my PhD, then I was applying for a postdoc. I was discussing with a professor in Kannada University. He was a ASC member of chapter 3-7. They wanted to develop Asian American Society of Civil Engineering, some codal provision for tsunami. He wanted to take me for that, and but unfortunately I could not join because I got some another program. But we need to develop such, include everywhere, in every country, so that we could have some development. So now coming toward the Indian breakwater, that is the Rubble breakwater. I have a sufficient amount of a sponsor project like DST, Ministry of Shipping also supported with 45 lakh. Like we have seen Fukushima nuclear power plant melting. So I have already developed. I have write a proposal for Department of Atomic Energy, Bhabha Atomic Center, to develop such a countermeasure so that in the future we may not face such a devastating melting down of any nuclear power plant in India or any other countries. So that is under review. So what is the difference? Indian breakwater. So generally two type of breakwater. This is the rubble mound breakwater, only dumped with a rubble, core, underlayer, outer layer. This is like a gravity or earthen embankment or earthen dam, and this is a composite breakwater. Rubble mound is there over the station. So India has this one. Behavior of both are completely different during earthquake and tsunami. Cause and frequency all different. So we have done this also. So, however, 57% of the breakwater all over the world has the rubble mound breakwater. So here we have done with I really blessed with a very good student, PhD student here. They have done day and night. We have developed a very good research lab here. We can have the infrastructure to conduct an earthquake simulation, earthquake checking table test. Over that, we can do the tsunami overflow test. We have done the lots of experiment to find out the mechanism and reason. So this is based on our experiment for rubble mound. Previously, I had discussed for cation type breakwater. This is completely rubble mound. So during earthquake, it will deform, and seismic inertia force will act. It will deform electrode. In the tsunami, during tsunami, what will happen? Scoring occurs from the top of the breakwater. We have done number of tsunami. Our student has done. Mr. Manu is working on that, and Mr. Akash is working for tsunami. Manu is working for here. So we found that escorting, I will show you the video also. So starting from top. So escorting is here. Then some amount of escorting can occur on the harbor side also. In addition, high impact force is acting on the breakwater. Seepage will be of course here because whole the breakwater is highly permeable. So finally escorting can occur 3 places. And then finally it can completely devastating damage. So we have developed some new technique. Here are some technique. Some models we have developed. This is the countermeasure. One for we have used for Gavian only. We have used for GeoVac. Also, we have used GeoGrid. Inside, we have used the wrapped phase GeoGrid reinforced model. So let me show you. This is the conventional model. So we have the 2 layers of the seabed, core layers, dense layer, seabed, loose soil layer, seabed upper layer. Then breakwater is made of the core layer, upper primary layer, upper layer, and the secondary armor unit. It looks like that. Then we are going to the first to this one. So this is the Gavian reinforced breakwater. Here we provide the 2 rows of seed coil. Seed coil was embedded till the dense soil layer. We didn't touch the core. We provided the Gavian both side, harbor side, as well as the sea side. Since we have found the starting crest was the main digging point for the escorting, so we provide the crown wall with shear key 1 or 2. So it looks like that with the Gavian reinforced. Now in the geobags. So similar to this one, we have used 2 rows of seed pile here, 2 layers of the seabed. We provide the core was same. We provide the geobags with the geogrid layers on this side, as well as the sea side, as well as the harbor side. It looks like that. We have the geogrid layer. We provide geogrid both the side with shear key. Here we have the wrapped face of the geogrid layers. So here we have 2 rows of seed pile, and both sides we have used the wrapped geogrid wrapped face, both primarily sea side as well as the harbor side, and it's look like this. So after that, we have done the shake table test for earthquake. We have done the physical model test, analytical study also, and numerical study simulation as well. Shaking table test we have done for check the earthquake. After that, we have done the tsunami overflow test, and we have developed some countermeasure. We check their effectiveness again by conducting the physical model test and check the mechanism by the numerical simulation. Right now, we are working as a 6 port breakwater of the Indian New Mangalore port. We have developed the countermeasure for Karnataka, Innor port Chennai in Tamil Nadu, Vizhinjam port in Kerala, LNG Swan port in Gujarat. Since Gujarat coming under high seismic zone, very close to the subduction zone, Muldwarka port Gujarat, and Tuna fishery port Tamil Nadu. This is some cross section we have used here, 18-meter depth, Vihangam Port, Kerala. This is the breakwater in Gujarat. Deepest this breakwater depth is 24 meter. So these are the material we use for the physical model test. This is armor unit. This is inner armor unit. We have used the crushed stones, core, 6 mm, sand, and the seed pile. We have used this geobags, geogrid, and these are the small gauge in a small size. The size was reduced as per the scaling law, so that if I use it, it will be practically in prototype scale, it will be practically available. So here in this experiment also, we have measured the vertical settlement, horizontal displacement, pore water pressure at this location, accelerometer, this yellow color, and the seed piles are there, numbers of geogrid layers, and this is the, here also we have given the 2 force yoke and 1 main check. Acceleration amplitude 0.1 G, 0.2 G, and 0.4 G. This is the first force yoke, second force yoke, and main yoke. So here I am comparing the Vihangam Port, Kerala, one example. So this is during the main shock earthquake, what is happening. This is the conventional breakwater. This is with our geogrid model. This is the conventional. So if I can say here during main shock, 50% reduction. Here in the case of vertical settlement, V1 and V2. Here horizontal displacement also, which is more than 30%, we can reduce by using this countermeasure. Now we are used to comparing the deformation by showing the picture. This is the before earthquake tsunami. This is unreinforced breakwater, reinforced breakwater. This is after the main shock. This is the completely damaged. We can see the breakwater came below the mean sea level. This is the seabed. The breakwater, it was up to this level, above the mean sea level, but come down. But in this case, it is resilient condition. Now I am going to show some our result for the tsunami. So we have developed a special type of equipment apparatus here. We have put the 2 numbers of water pump for inletting and outletting the water chamber. Here we have made the seabed and the breakwater model. Through that, water is allowed to come here, striking here, going back, coming here, and this is sucking back, going back again. This water is coming and this is going to circulation, so that there is no reflection of the tsunami wave. In that way, we can design the real earthquake. At the same time, we are allowing to overflow, so that it can, if the coming in the future tsunami exceeded the design height of the tsunami, then what will happening to my model, our model that we wanted to show. So in this edition, my PhD student, he has developed a very fantastic robotic file mapper, purely developed by him. This is very useful. And by using this, not only this research, but another work also, we can able to quantify the amount of scoring or any deformation of any models by the moving. This is a new advanced automated programmable profile data we can develop. It will develop in our Geo-Disaster Prevention Lab in ITK. This is a robotic profile, and few industry people was very much interested to adopt this for field study. So here, I'm not talking much about that. Coming to the tsunami overflow test. So how much settlement, how much we have to save. So we can see this is a conventional type breakwater. This is inward port. The tsunami generation by cyclic method and almost negligible vertical settlement with this Gabion unit. Reinforced breakwater was there. The lateral displacement was also negligible. And we have the using more profile mapper. They have done. This is the conventional breakwater. This much scoring occur. This is the before earthquake, before tsunami. This is after tsunami. Difference of this much scoring occur. But this is for the reinforced breakwater, almost negligible. That's why this is slow. And if you quantify, you can able to find out how much cubic meter, how much volume is covered. This much volume is covered for conventional breakwater. However, reinforced breakwater no scoring, and this is the, I would like to show the, this is the dam break model for the our Indian breakwater we have done. Upper portion is the conventional breakwater. lower portion is the gabion reinforced breakwater. We can see very clearly the upper one conventional breakwater was completely collapsed, washed away by the tsunami, but lower breakwater, reinforced breakwater under same 100% same composition, it is resilient in a stable condition. So this is just for one indication purpose. We have done so many tests, and based on that, we have using their data. This is just for one example. Recently, we have done tests to show the how it works in the lab condition. So this is the numerical simulation by Plexus, like 3D. We have done for the numerical simulation, especially for seepage analysis. This is the conventional model, high seepage throughout the breakwater, because this is rubble mound made of the big rubble and boulders, so high seepage. But here we can see the less seepage. So what is the need of research, future research? So I am exceeding. I will quickly finish. I'm very sorry. Quickly finish. So this is till now I have finished. So I have a urge for you, all the researcher, and request, please come forward. For example, this is a pioneer example. One building failed due to, even it was there, maybe it was earthquake resistant, because in Japan, most of the building are earthquake resistant design. Even it failed. So please come forward. Even if within 50 lakhs or 60 lakhs, we can able to develop a tsunami flume, and we can have some study to go forward and give some recommendation. Like Cello Foundation also it followed what we can introduce to our civil society, civil engineers, or our whole human society to protect our community, our building, our life from tsunami. It is at, in fact, next level of devastation against the, beyond the level of the earthquake. So we have to start from the beginning. Some research has been started, but it needs large number of research. Then we can find the, open the more layers of the invisible things, and we can able to design guidelines. I'm happy to quote here. Sometime back, I had an opportunity to talk our DGM of IS code for making Mr. Sri Sanjay, my missing the, but he was happy to offer me to provide some recommendations, so that those recommendations for can be added in the IS code, so that if someone or our government or even the nuclear power plant or Department of Atomic Energy or some hospital, some government society want to make earthquake or tsunami resistant resilient structure, they can able to build, or at least we can able to suggest, yeah, you can go in this way, that will insert resiliency, sustainability against your tsunami. So this is the same building here. You can see the pile foundation work completely done. So what is the conclusion? We have the very limited research work has been done for mitigating the tsunami damage. We need lots and lots of the research. And my dear friend, there are lots of scope and R&D in geo-disaster mitigation, as well as I have discussed geo-environmental issue is also big. Once it filled with the debris, lots of the bodies, human bodies, the soil will be a thick layer mixed with biodegradable, non-degradable like metallic plates, wood logs, biodegradable, concrete, non-biodegradable, steel rod, pillars, animals body, human body, many things are good. So those area, those soil will be not suitable for either irrigation, either farming or building a small structure also. We need a next level that is going to impure pollute our groundwater table also. So we need a really good amount of research there. Only at the same time, only a structural mitigation measure is not sufficient to meet the requirement of the disaster reduction against high level of tsunami. So approaches to countermeasures should be include not only the structural measure, but the non-structural measure. We have to develop some countermeasure, as well as we have to develop some monitoring system, warning system, evacuation route. Here we have to decide, so that in that case, people can follow the active route and run away. And there should be good amount of public awareness program and training that really works. I'm going to show you one example. So what happened? This is the last slide here. This is for the safety purpose I'm showing. Before that, I'm going to show you a small story. In 2004, Indian Ocean earthquake tsunami, Tilly Smith, one small girl, she was British and she was in Phuket, Thailand for a vacation with their parents. And she was spending there, but she learned something about tsunami in the school. She found that there was tsunami coming in that beach. So somehow he convinced her parents, and their parents ran away to the hotel. And luckily, there was one Japanese staff in this hotel. He was knowing about the tsunami. He convinced with that girl, Timmy Smith, logic, and they called the police, and that police, Thailand police, has evacuated that beach, and due to that, they can able to save thousands of the people with that. So please be very careful. Please watch this very carefully. This is for life-saving in case you are in some tsunami prone
Let's
area.
put some basic information on the table. While more common in the Pacific, a tsunami can strike any coast, anytime.
Sound is
It's one of the most destructive forces in nature. A series of waves, usually caused by an undersea earthquake.
sound is audible.
Powerful, fast-rising floodwaters can smash everything in their path. Even small tsunamis can be dangerous, especially to swimmers, surfers, and boats in harbors. But there are ways you can prepare. First, understand the warnings. If an official warning is issued, do what it says. Just as important, pay attention to warnings Mother Nature provides. You may feel a strong or long earthquake. You may see the ocean suddenly rise or fall, or hear a loud roar. If you experience any of these, a tsunami could be coming. Protect yourself. Quickly move to high ground or inland away from the water. Stay out of the tsunami hazard zone until officials tell you it's safe. The first wave may not be the last or the largest. Dangerous currents are possible for several hours or days. Prepare yourself by doing a little homework. Think of the places where you spend your time and map out routes to safe places, high ground or inland, away from the water. Practice walking these routes so they become familiar. Be prepared and stay safe.
Thank you. So this number we are with due permission from Professor Reddy. We are organizing one conference in Japan. Professor Zarika is the organizing chairman. CREST 2023. If you get opportunity, please join. We're happy to welcome you there. And this is the website detail. You can write CREST 2023. You're able to find out. Thank you very much for lesson. Your really patience listening. So this is the last my message. This is the warning signboard for tsunami. So in your lifetime, if you will find some beach, this type of sign is there. That means you are in the earthquake or tsunami hazard zone. So please don't need to worry. Please be prepared. Find out the island in case of such thing happen. So please be prepared. Be safe. I pray safety for all the human beings against such a natural disaster. Thank you. Thank you very much for all of you. And I'm again very much thankful, Professor Reddy, to allow me. It was a great opportunity. It was really honor for me so that I can share this small basic information and the need of research we really need for our human beings. Thank you very much, sir.